Alright, let's dive straight into the fascinating world of how materials behave under stress. We're talking about the fundamental principles that govern how things bend, stretch, and ultimately fail. So, what kind of forces are we actually talking about? Loads. Think of it like this. There's your dead load, the constant, unchanging weight, like the roof of a house just sitting there. Then you've got live loads, the dynamic ones, like a truck rumbling across a bridge. That's a live load. Imagine a sudden impact, like a hammer blow. That's impact or shock load. And finally, fatigue loads. These are the sneaky ones where the force changes direction and magnitude over time, like the vibrations in a car engine. Each type puts a different kind of stress on the material. Let's get more specific. In engineering, a load is basically any external force acting on a structure or mechanism during its normal operation. We often categorize them based on their nature. Dead loads are static. Think the weight of the building itself. Live loads are variable, like people moving around or vehicles passing by. And then we have the types of forces acting on the material: tensile, pulling apart; compressive, pushing together; and shear, sliding past each other. We usually consider tensile forces as positive and compressive as negative, a simple sign convention to keep things clear. Now, how do materials react to these loads? They have different personalities. Elasticity is like a spring. You pull it, it stretches; let go, it snaps back. Rubber is super elastic. Plasticity is like clay. You deform it, it stays deformed. Aluminum is quite plastic. Brittleness is like glass. It breaks suddenly without much warning. Cast iron is brittle. Malleability is the ability to be hammered into thin sheets, like lead. And ductility is the ability to be stretched into wires, like copper. Notice how some properties are opposites? A material can't be both perfectly brittle and perfectly ductile at the same time. Okay, let's talk about stress. Imagine you're squeezing a toothpaste tube. The internal resistance offered by the tube material against that squeeze, per unit area, that's stress. It's the intensity of the internal forces resisting the external load. Think of it as the material's internal fightback. For a simple case, like pulling a bar, we calculate direct or normal stress, sigma, by dividing the applied force P by the original cross-sectional area A. Simple formula: sigma equals P divided by A. The units are typically newtons per square meter, or pascals. Stress isn't just one thing, it comes in different flavors. We broadly classify it into normal stress and shear stress. Normal stress acts perpendicular to the surface, like the tension in a rope or the pressure on a piston. Shear stress acts parallel to the surface, like trying to cut paper with scissors. Normal stress itself splits into two: tensile stress, which pulls, and compressive stress, which pushes. We'll also see indirect stresses like torsional and bending, and how they combine. This diagram gives a nice overview of the hierarchy. Let's zoom in on normal stress. First up, tensile stress. Imagine pulling on a rubber band. It gets longer, right? That stretching force per unit area is tensile stress. It's the internal resistance trying to prevent the material from getting longer. The amount of stretching relative to the original length is called tensile strain. Look at figure A, B, and C. The bar is pulled by force P. Internally, there's a resisting force R. The stress sigma is simply P divided by A. The strain E is the change in length dl divided by the original length L. Easy peasy. Next, the counterpart to tension, compressive stress. Think of pushing down on a column. It gets shorter, and it pushes back. That pushing force per unit area is compressive stress. Again, the internal resistance is key. The shortening relative to the original length is compressive strain. The formula looks identical to tensile stress. Sigma equals P divided by A, but the effect is different: pulling versus pushing. Figure A shows the push, and the internal forces are resisted. Simple concept, crucial difference. Now for something different: shear stress. Forget pulling or pushing directly. Think of cutting a deck of cards. You slide the top half against the bottom half. That sliding force per unit area is shear stress. It's the internal resistance to that sliding motion. It acts tangentially to the surface. Look at these diagrams, forces P acting tangentially across the section, trying to make the material slide off. This is super common in bolts, rivets, and beams. Ever twisted a bottle cap? That's torsion. Torsional stress happens when a member is twisted around its axis. One end is fixed, the other rotates. Imagine a shaft connected to a seized bearing while the other end tries to rotate. The shaft twists, and that internal twisting force is torsional stress. Think of drive shafts in cars or turbine blades. The symbol for torsional stress is often tau, similar to shear stress but representing the twisting component. Bending. Think about a diving board. You stand on one end, it bends downwards. That bending action creates internal stresses. The top fibers are compressed, the bottom fibers are stretched. The stress varies along the height of the beam. We calculate bending stress, sigma b, using the formula sigma b equals my divided by I. Here, m is the bending moment, y is the distance from the neutral axis, and I is the moment of inertia. Don't worry too much about the details now, just know it's a critical calculation for beams and columns. We'll dig deeper into this later. Alright, we've talked about stress, now let's talk about strain. If stress is the intensity of the internal force, strain is the actual deformation caused by that stress. It's the ratio of the change in dimension to the original dimension. Since it's a ratio, it's dimensionless. Think of it as the percentage of deformation. We have different types: tensile strain for stretching, compressive strain for shrinking, volumetric strain for volume change, and shear strain for angular distortion. Look at the parallelogram, that's shear strain, the angle gamma xy. Let's break down strain further. Based on the load type, we have tensile, compressive, and shear strain. Based on whether the deformation is temporary or permanent, we have elastic or temporary strain, which disappears when the load is removed, and plastic or permanent strain, which stays. And based on the direction, we have linear strain, change in length, lateral strain, change in width or diameter, and volumetric strain, change in volume. For tensile strain, epsilon t, it's simply the increase in length, delta L, divided by the original length, L. Easy ratio. Compressive strain, epsilon sub c, is the decrease in length, delta L, divided by the original length, L. Same formula, different direction of force. Now, shear strain. Remember those parallel forces trying to slide past each other? The resulting angular deformation is shear strain. Look at the pin joint example. Forces P try to shear the pin, or the plates. The shear strain, gamma, is related to the angle of deformation, phi, or the ratio of displacement x over length L. It's the measure of how much the material has been sheared. Let's revisit those classifications. Temporary or elastic strain is the good stuff. It vanishes when the load goes away. Permanent or plastic strain is the bad stuff. It stays, meaning the material is permanently deformed. Linear strain is the change in length along the direction of the load. If it's tensile, it's elongation. If compressive, it's shortening. The formula is delta L divided by L. This is the primary deformation we often focus on. Lateral strain is the change in dimensions perpendicular to the load direction. So, if you pull a bar, it gets longer linearly, but it also gets thinner laterally. The lateral strain is the change in breadth or diameter divided by the original breadth or diameter. It's always opposite in sign to the longitudinal strain. Volumetric strain, also known as bulk strain, is the total change in volume divided by the original volume. When you apply pressure, the volume changes. This is important for fluids and gases, but also relevant for solids under hydrostatic pressure. Now for a cornerstone concept, Hooke's law. This is the magic behind springs and many elastic materials. It states that within the elastic limit, stress is proportional to strain. The constant of proportionality is Young's modulus, denoted by E. So, sigma equals E times epsilon. Think of E as the stiffness of the material. A higher E means more stress for the same amount of strain. Materials that follow this perfectly, are said to obey Hooke's law. Similarly, for shear, we have the shear modulus G, where tau equals G times gamma. And for volume changes, the bulk modulus K. These moduli are fundamental material properties. Let's revisit lateral strain. When you pull a rectangular bar, it gets longer and thinner. The decrease in breadth, delta B, or depth, delta D, relative to the original breadth, B, or depth D, is the lateral strain. The key takeaway here is that lateral strain is always opposite to the longitudinal strain. If you stretch it, it shrinks sideways. If you compress it, it bulges outwards. This relationship is quantified by Poisson's ratio. Longitudinal strain, also known as linear strain, is the change in length along the direction of the applied load. If you pull the bar, delta L is positive, it's tensile. If you push, delta L is negative, it's compressive. The formula is simply the change in length, delta L, divided by the original length, L. This is the primary measure of deformation in tension or compression. The diagrams show the bar getting longer and thinner. Poisson's ratio. This is a really neat property. It's the ratio of the lateral strain to the longitudinal strain. For most materials, it's a positive number between 0 and 0.5. It tells you how much a material shrinks sideways when you pull it, or how much it bulges sideways when you push it. It's a constant for a given material within the elastic limit. So, mu equals lateral strain divided by longitudinal strain. There's also a modular ratio, which is just the ratio of the Young's modulus of one material to another. Useful for comparing stiffness. Linear elasticity is the ability of a material to return to its original shape and size after the load is removed, provided the deformation was within limits. Elastic limit is that critical stress level. Go below it, and the material is perfectly elastic. Exceed it, and even if you remove the load, some permanent deformation remains. It's like stretching a rubber band too far. It might not snap back completely. Understanding this limit is crucial for safe design. This is the famous stress-strain curve. This graph tells us the story of a material's life under tension. Look at structural steel. From O to A, it's perfectly linear, Hooke's law in action. That's the elastic region. Beyond A, the proportional limit, it still behaves elastically, but not linearly. Then comes yielding, points B and C, where the material starts to deform plastically with little increase in stress. After yielding, it hardens, reaching a peak at the ultimate strength, D. Finally, necking occurs, the cross-section reduces dramatically, and it fractures at E. This curve is gold for engineers. To get that curve, we use a standard specimen. It has specific dimensions: grip length for holding, gauge length, LO, for measuring deformation, and tapering length for smooth transition. We measure the original length, LO, and area, AO. Then, we pull it until it breaks. The percentage increase in length at fracture, percentage elongation, and the percentage reduction in cross-sectional area, percentage reduction in area, are key measures of ductility. High values mean the material is very ductile, like copper or mild steel. Low values mean it's brittle, like cast iron. Here's the visual journey of a ductile specimen during a tensile test. Start with the original length, L0. As we pull, it enters the elastic region, then the plastic region. Initially, the deformation is uniform. But as the stress increases, the material starts to neck down. That's the localized reduction in cross-section, shown here. Eventually, the neck can't support the load anymore, and it fractures. This necking phenomenon is characteristic of ductile failure. This slide reinforces the stages we saw earlier. Elastic deformation, then plastic deformation, which is further divided into uniform and non-uniform. The maximum stress reached is the ultimate tensile strength. The point where significant plastic deformation begins is the yield strength. And the final fracture point is the fracture strength. The slope of the initial linear part is the Young's modulus, E. Understanding these points is vital for designing components that won't fail unexpectedly. When we plot the stress-strain curve, we usually use the original area and original length. This gives us engineering or nominal stress and strain. But as the material deforms, especially in tension, the actual cross-sectional area decreases and the gauge length changes. Using the instantaneous values gives us true stress and true strain. True stress is higher than nominal stress after yielding because the area is smaller. True strain accounts for the changing length. While engineering values are simpler, true values give a more accurate picture of the material's behavior, especially in the plastic range. Different materials have vastly different stress-strain curves. Look at this comparison. High-carbon steel shows that classic yield point and necking. Cast iron is brittle, it goes straight to fracture with almost no plastic deformation. Aluminum is ductile, showing significant elongation before fracture. Concrete is also brittle, but it has a different failure pattern. Understanding these differences is crucial for selecting the right material for the job. You wouldn't use cast iron for a bridge cable, would you? What about materials that don't have a clear yield point, like aluminum or brass? We use proof stress, or offset yield stress. We draw a line parallel to the initial elastic line, but offset by a standard strain, usually 0.2%. Where this offset line intersects the actual stress-strain curve, that's our proof stress. It's an arbitrary definition, but it provides a practical measure of the yield strength for these materials. It's the stress at which the material has undergone a specified amount of permanent deformation, typically 0.2%. Factor of safety, or FOS, is absolutely critical in engineering design. It's the ratio of the maximum stress the material can handle to the working stress it will actually experience. For ductile materials, we usually use the yield stress as the maximum. For brittle materials, we use the ultimate stress. Why do we need it? Because real-world conditions are messy. Material properties vary, loads aren't always perfectly predicted, manufacturing isn't perfect. FOS is our buffer against uncertainty. A FOS of 1 means no safety margin, bad idea. Typically, we aim for FOS values greater than 1, often 2 or more, depending on the application. Sometimes, especially in aerospace or other high-stakes industries, people talk about margin of safety, or MOS. It's closely related to factor of safety. Often, MOS is defined as factor of safety minus 1. So, if your FOS is 2, your MOS is 1. It represents the additional capacity beyond the design load. Another way to think about it is the ratio of failure load to design load, minus 1. It's essentially a measure of how much extra load the structure can take before failing, expressed as a percentage or fraction. It's another way to quantify that safety buffer. This chart summarizes a bunch of key mechanical properties we'll encounter. We've touched on some already: strength, ductility, brittleness, toughness, resilience. But there's more. Hardness, stiffness, fatigue, creep, wear resistance, corrosion resistance. The list goes on. These properties define how a material performs in service. Understanding them helps us choose the right material for the right job, whether it's building a skyscraper, a bicycle, or a microchip. Let's quickly recap some of these properties. Strength is the ability to resist deformation or failure. Ductility is how much it can stretch or bend before breaking. Brittleness is the opposite, breaking easily without much deformation. Toughness is the ability to absorb energy and plastically deform without fracturing. Think of it as resilience plus ductility. Resilience is specifically about absorbing energy elastically, storing it, and releasing it, like a spring. Proof resilience is the max energy stored elastically. Modulus of resilience is that energy per unit volume. Hardness is resistance to surface indentation or scratching. Think Mohs scale for minerals or Brinell hardness for metals. Hardenability is how deep a material can be hardened by heat treatment. Malleability is the ability to be flattened into thin sheets under compression, like gold leaf. Creep is slow, permanent deformation under sustained load, especially at high temperatures. Slip is the atomic mechanism behind plastic deformation. Fatigue is the weakening and eventual failure due to repeated loading, even below the static strength. Sharp corners and holes are notorious fatigue starters. Here's a rapid-fire summary of some mechanical properties. Brittleness, shatters easily. Bulk modulus, resistance to volume change under pressure. Coefficient of restitution, bounciness after collision. Compressive strength, max stress before crushing. Creep, slow deformation over time. Ductility, ability to stretch. Durability, wear resistance. Elasticity, ability to return to shape. Fatigue limit, max stress for infinite cycles. Flexibility, ability to bend. Flexural modulus, stiffness in bending. Flexural strength, strength in bending. Fracture toughness, resistance to crack propagation. Friction coefficient, resistance to sliding. Continuing our whirlwind tour. Hardness, scratch resistance. Malleability, flattening ability. Mass diffusivity, how easily atoms move through a material. Plasticity, permanent deformation without breaking. Poisson's ratio, lateral to axial strain ratio. Resilience, energy absorption in elastic deformation. Shear modulus, stiffness to shear. Shear strength, max shear stress. Slip, atomic dislocation motion. Specific modulus, stiffness per unit density. Specific strength, strength per unit density. Specific weight, weight per unit volume. Stiffness, resistance to deformation. Surface roughness, texture. Tensile strength, max stress before stretching failure. Toughness, energy absorption before fracture. Viscosity, fluid resistance to flow. Yield strength, stress at which plastic deformation starts. Young's modulus, stiffness to tension or compression. Strain energy is the work done on a material by external forces, which gets stored inside the material. If it's within the elastic limit, this energy is recoverable. That's resilience. Proof resilience is the maximum amount of elastic energy a material can store. The modulus of resilience is that energy per unit volume. Think of it as the material's capacity to store and release energy elastically. It's related to both the material's strength and its elasticity. So, how do we actually get that precious stress-strain curve? We use a universal testing machine, or UTM. It clamps the standard specimen, applies a controlled tensile force, and measures the resulting elongation. We record the load and the corresponding deformation at many points until the specimen breaks. By dividing the load by the original area, we get engineering stress. By dividing the deformation by the original gauge length, we get engineering strain. Plotting these pairs gives us the curve. It's a fundamental experiment in materials science. Here's the stress-strain curve again, with key points labeled. OA is the proportional limit, where stress is directly proportional to strain. B is the upper yield stress point, the start of yielding. C is the lower yield stress point, the plateau of yielding. D is the ultimate stress point, the maximum stress the material can withstand. E is the fracture point, where the specimen breaks. The region between O and B is the elastic behavior. The region from B to D is the plastic behavior, where permanent deformation occurs. The region after D involves necking and eventual fracture. Let's revisit the basics. Stress is the internal force per unit area. When a force F acts on a cross-section A, the stress sigma is approximately F divided by A. This is the average stress. In reality, it's distributed. Look at the diagrams. The force F is applied, and the material resists internally. The blue arrows represent the internal stress trying to hold the material together. The red arrow is the external force. We're interested in the internal fightback, the stress. Here's a real-world example. On the left, a machine applying compressive load. On the right, a concrete column that failed in shear. Notice the crack runs diagonally, not perpendicular to the load direction. This highlights that even though the primary stress might be normal, the material can fail along a different plane, especially under shear conditions. It's a reminder that failure analysis can be complex. Principal stresses and principal planes. Imagine a block of material under stress. The stress isn't always acting on the faces we initially defined. There are special orientations, called principal planes, where the shear stress is zero. On these planes, the stress is purely normal, and these normal stresses are called principal stresses. Finding these is important because it helps us identify the maximum and minimum normal stresses acting on the material. In reality, stresses often act on inclined planes, not just the principal ones. The normal plane is perpendicular to the force axis. The oblique plane is at an angle theta. When we analyze stress on these oblique planes, we need to resolve the forces and find the normal stress sigma n and shear stress tau acting on that plane. This is crucial for understanding stress distribution in complex geometries. Let's derive the stress on an oblique plane. Consider a force P acting on a cross-section A. We want to find the stress components on a plane inclined at angle theta. The normal stress, sigma n, on the oblique plane is sigma times cosine squared theta. The shear stress tau on the oblique plane is sigma times sine theta times cosine theta. These formulas tell us how the normal and shear stress components change as we rotate the plane. At theta equals 0, we're back to the normal plane. At theta equals 45 degrees, the shear stress is maximized. We can generalize this. We can analyze stress states for e. A member subjected to direct stress in one plane only. 2. A member subjected to direct stress in two mutually perpendicular planes. 3. A member subjected to simple shear stress only. 4. The general case, direct stress in two mutually perpendicular directions plus simple shear stress. These are the fundamental building blocks for analyzing more complex stress states. For the general case, where we have direct stresses sigma 1 and sigma 2 in two perpendicular directions and a shear stress tau, the normal stress sigma n and shear stress tau acting on an oblique plane at angle theta are given by these equations. They look complicated, but they're just extensions of the simpler cases. They account for the combined effects of the direct stresses and the shear stress on the inclined plane. Remember principal planes? Where shear stress is 0. We can find the orientation of these planes using the general shear stress formula. Set sigma t equals 0 and solve for theta. This gives us the tangent of twice the angle theta, which is 2 times tangent theta equals 2 times tau divided by sigma 1 minus sigma 2. This equation tells us the angle of the principal planes relative to the original axes. There are two principal planes, 90 degrees apart. These trigonometric identities help us find the exact values of sine and cosine for the principal angles. The triangle illustrates the relationship. Using these, we can determine the exact angles theta p1 and theta p2 where the principal stresses occur. The formulas for sine and cosine of 2 times theta involve the principal stresses and the shear stress. This allows us to precisely locate the principal planes. Once we know the angles of the principal planes, we can substitute them back into the general stress equations to find the principal stresses themselves. The major principal stress, sigma 1 prime, is the maximum normal stress, and the minor principal stress, sigma 2 prime, is the minimum normal stress. The formulas involve the original stresses sigma 1, sigma 2, and the shear stress tau. These are the maximum and minimum normal stresses acting on the material. Besides principal stresses, we often care about the maximum shear stress. Where does it occur? We find it by maximizing the shear stress equation, sigma t, with respect to theta. Take the derivative of sigma t with respect to theta, set it to 0, and solve for theta. This gives us the angle theta s where the maximum shear stress occurs. Interestingly, the angle of the maximum shear plane is 45 degrees away from the principal planes. Substituting the angle theta s where the maximum shear stress occurs back into the shear stress equation gives us the maximum shear stress, sigma t max. The formula is sigma t max equals 1/2 times the square root of open parenthesis sigma 1 minus sigma 2 close parenthesis squared plus 4 tau squared. This is the maximum shear stress acting on any plane within the material. It's half the difference between the principal stresses, adjusted by the shear stress. This is crucial for predicting shear failure. Let's quickly revisit the specific cases. 1. Direct stress in one plane, sigma 2 equals 0, tau equals 0.2. Direct stress in two mutually perpendicular planes, tau equals 0.3. Simple shear stress. Sigma 1 equals 0, sigma 2 equals 0.4. The general case, sigma 1, sigma 2, and tau are all non-zero. Understanding these simplifies the analysis for many practical problems. Case 1. Direct stress in one plane, sigma 2 equals 0, tau equals 0. The formulas simplify significantly. The normal stress on the oblique plane is sigma n equals sigma 1 times cosine squared theta. The shear stress is sigma t equals sigma 1 times sine theta times cosine theta. This is the simplest case, just pulling or pushing in one direction. Case 2. Direct stress in two mutually perpendicular planes, tau equals 0. The formulas become sigma n equals sigma 1 plus sigma 2 over 2 plus sigma 1 minus sigma 2 over 2 times cosine 2 theta. And the shear stress is sigma t equals sigma 1 minus sigma 2 over 2 times sine 2 theta. This is like biaxial tension or compression, common in thin plates or membranes. Case 3. Simple shear stress, sigma 1 equals 0, sigma 2 equals 0. The formulas simplify to sigma n equals tau times sine 2 theta. And the shear stress is sigma t equals minus tau times cosine 2 theta. This is the case for pure shear, like in torsion or shear bands. The maximum shear stress is simply tau, occurring at theta equals 45 degrees.